here we look at IO model, and it's an example of a more realistic model of computation. There are many motivations to consider this model. In particular, when you have a large data set, typically it resides on the disk. So therefore, if you want to do anything with that data, you need to consider this disk operations, because disks are quite slow. Even though technically disks only a constant factor slower than the memory, the constant is relatively big. So if you ignore that constant, then you have an algorithm that doesn't match, that has a gap between theory and practice. Okay, so we want to model a disk, and we want this model to be good and to be useful, and we also need to analyze the algorithm with this model. The thing is that disk is a very complicated device. If you look inside a hard disk, you'll see that it has multiple reading heads. So this is a reading head that can read data. But disk is composed of a bunch of essentially disks that they have that store data. And in any hard disk, you don't have just one disk that stores data. You have multiple of them, and between each one of them, there is a reading head that can read things. Disk spins and can spin by fixed maximum speed. And of course, different disks, hard disks could have different speeds. Obviously, if the faster it rotates, it's better. But because of the existence of this rotation as well as this arm, there are two types of latency. And latency means how long it takes for you to read data. So for example, if you want to read the data that is, let's say over here, you have to wait for the disk to spin until this point of data is close to the arm. But on top of that, this arm also needs to move to be at the right position to read the data as this point slides under it. So that these two takes different amount of time. So you have the rotational latency, how long it takes for the disk to rotate, and seek time, how long it takes for your arm to move. And on top of that, the rotational latency is variable, because if the disk is spinning with a constant speed, then the points that are on the edge, they move faster. Okay, so in other words, this point that is over here moves at a slower speed. Okay, from angular point of view, so the angular velocity is the same, but the actual velocity is different. Okay, so in other words, you can fit more data over here. The data, let's if you fit so basically you can fit a larger amount of data over here, and these points of data, they spin, they move much faster. Okay, and actually when it comes to very applications where you need high performance, typically people don't use the inside of the disk. So maybe this part of the disk, we just keep it empty and we store everything towards the edges, because those are the ones that they move faster. And on top of that, there's also the notion of data density. And let's say in 1 unit area of the surface, how much data, how many bits we can pack. So one way to model disk is to keep a parameter for everything, right? So you have a main memory of size m, you have a disk that has h heads, it has a rotational speed of r, the arm accelerates with acceleration a and deaccelerates with acceleration a prime. It has a data density d per unit of area, and has a data transfer rate t, so it how fast it can read data. Okay, so that's a lot of parameters, but for sure this is going to be a very realistic model. But the problem with this realistic model is that it's very difficult to do any sort of analysis. So for example, let's say we have a disk that stores n numbers, n integers, starting from the innermost track and going all around, right? So you have a full disk of information, stores a large number of numbers. You can run quicksort on this and now analyze it. Okay. If you probably don't even need to think about this. It seems like torture to analyze even a simple algorithm such as quicksort on such a model. First of all, any sort of analysis will need to have all of these parameters. And then you need to do the recursion analysis, you need to do the partial analysis. Actually, it looks quite impossible, to be honest. So we need to do much better. We need to have a better model. And that's what we're going to do next.